The largest volcanic eruption in recorded history was the eruption of Mount Tambora in 1815. Its eruption column rose more than 9,000 meters into the sky and cooled the planet by about 3 degrees Celsius, triggering the infamous year without summer. But Tambora only holds that title within recorded history. The largest eruption on Earth in the last million years was far greater and far older. That was the Toba eruption, which occurred roughly 74,000 years ago. Its eruption column blasted material more than 32 kilometers high and cooled the global temperature by as much as 5 degrees Celsius. The aftermath of Tambora is easy to understand. It happened in a world of written records, letters, harvest log paintings, and eyewitness accounts. But Toba happened long before satellites, before thermometers, before instruments, and even before writing itself. There were no alarms when it erupted. The sky darkened, the ground shook, and humanity had no way to record what was happening. So how do scientists today describe the eruption in such detail? How do they know how powerful it was, how high the ash rose, how hot the magma burned, and even how much planet cooled afterwards? In my previous video, I explained how scientists determine how old something is. In this video, we are answering the next question. How do we know what actually happened? At first glance, it sounds impossible. But the truth is simpler and more unsettling. The Earth never erased the evidence. It archived it. When a volcano erupts, it doesn't just release energy and disappear. It physically rearranges the planet. Ash, rock fragments, and gases are hurled into atmosphere and eventually settle across continents, oceans, lakes, and ice sheets. Over time, these materials form distinct layers, quietly buried as new layers accumulates above them. Each volcanic eruption produces ash with unique chemical fingerprint determined by the magma beneath the volcano. By analyzing the chemistry, scientists can match ash layers found hundreds or even thousands of kilometers apart from the same eruption. When the same layer appears across vast regions, its thickness and distribution reveals how much material must have been expelled. Closer to the volcano, and the land itself tells even a deeper story. Some massive eruptions drain underground magma chambers so completely that the surface collapses, forming enormous depression called calderas. The size of these structures provide direct evidence of how much magma was released. By combining these measurements with well-tested eruption classifications, scientists can reconstruct eruptions that occurred long before the written record existed. Ash doesn't drift randomly through the skies. Its movement is governed by gravity, particle size, and atmospheric circulation. Large particles fall quickly. Fine particles can remain suspended for weeks and travel across the planet. When relatively large ash fragments are found far from their source, scientists know they must have been carried by powerful winds high in the atmosphere. The direction of ash spread matters too. Different wind layers move in different directions, and ash deposits often shows multiple dispersal patterns at once, evidence that the eruption injected material into several atmospheric layers simultaneously. Some of the strongest evidence comes from polar ice. Volcanic sulfur gases only spread globally if they reach the stratosphere, where rain can't easily wash them out. When the sulfate layer from the same eruption appears in the ice cores from both hemispheres, it confirms that the plume reached the extreme height. Using physical plume models constrained by these observations, scientists determine the minimum height an eruption must have reached, not to the exact meter, but precisely within the limits. The rock themselves also remember heat. As magma cools, minerals crystallize, and each mineral can only form within specific temperature ranges. Those temperatures become locked into crystal structure at the moment of solidification. Some crystals trap tiny droplets of molten magma inside them before eruption. These melt inclusions preserve the original temperature, pressure, and gas content of the magma deep underground. In laboratories, scientists reheat these samples under controlled conditions until they recreate the original state, revealing the temperature at which they formed. Because of these temperature ranges are well established and confirmed by modern eruption, the results are consistent and repeatable. The heat of ancient eruption isn't guessed, it's measured. When a massive eruption injects sulfur into stratosphere, they form aerosols that reflect sunlight back into space. Less sunlight reaches the surface and the planet cools. That cooling leaves fingerprints everywhere. Trees respond immediately. In colder years, growth slows, producing narrow rings. When trees across different continents shows the same pattern in the same year, it signals a global climatic event. Ice cores tells the same story, capturing both volcanic sulfur and changes in oxygen isotopes linked to the temperature shifts. Oceans respond too. Corals grow layer by layer, and the chemistry of these layers reflect water temperature. Lakes and marine sediments preserve biological changes triggered by cooling. Each of these records is independently calibrated using modern instrumental data. Finally, climate models are used to test whether the amount of volcanic material inferred from geology can reproduce the cooling seen in these natural archives. When the model matches the physical evidence, confidence grows. So, how do we know what happened tens of thousands of years ago? Because nothing truly disappears. The sky left traces in the ice. The cold slowed the trees. The heat shaped the crystals. The ash traced the winds. And the ocean recorded the aftermath. The earth does not observe events and forgets them. It records them patiently, precisely, and without intention. Long before humans learned to write history, the planet was already doing it. Science is not discovering the past. It is learning how to read what was always there. And if an eruption like this happens today, how do you think it would change the world? If you enjoyed this video, don't forget to hit like and subscribe. And tell me in the comment what topics you want to see in the future videos.